Today we will look at example of ECG and talk about it. However, the ECG is not complete because the lead 4, 5 and 6 there are not clearly seen. But we will discover how far we will go. So let's start from the basic thing, that is uh, let's determine the heart rate and rhythm at first. So we take a rhythm strike. So this is our lead 2, you see here, this is our rhythm strike. So if you see two peaked R waves, here is one and here it is one, and another it is one here, and here it is one. So if you compare here, so here one big square box, 2, 3, and somehow 3.5. Similarly here, half, 1, 2, 3. So it pretty seems that they are like equal, equidistant. Another example also we can see here. So 1, 1, 2, 3. So pretty 3.5. And here also you can take it must be pretty here, 1, 2, 3, and somehow 3.5. So it seems like the heart rate here, it is like the rhythm here, it is pretty normal. So for that, now to calculate the heart rate, what formula you can use? Now we are going to calculate the heart rate. So if the heart rate is normal, then one basic for a fast calculation, what formula you can use is 300, 1500, 100. Some of the friends, they asked me why that formula was used, why it's always like that, and in another formula there is a formula like 1500 divided by small square box. One thing I would like to make you clear: suppose this is a big small, this is a big square box, okay. Let me draw it, a nice one. So you see here, this becomes square box, and in this square box, so there are like 25 small square box. So line will go like this and another line will go like this, so there will be 24 small square box. So one thing you need to keep in mind, that one small square box, when it passes through the ECG stripe, so it will take 0.04 second. So this thing you need to keep in mind. So one small square box will take 0.04 second. So 1 second will be equal to 1 divided by 0.04, isn't it? So in 1 second, 1 by 0.04th part of the square will be covered. So basically in 60 seconds, so in 60 seconds, so in 60 seconds, so in 60 seconds you will travel. So in 60 seconds, let me calculate it fast. So in 60 seconds, that is the time, the part covered in 1 second multiplied by 60. So 1 divided by 0.04 will be 25. So 25 into multiplied by 60, isn't it? So this becomes 25 into 60, so it is 1500. So you see, that is in 60 seconds, that means in 1 minute. So that is equivalent to heart rate, isn't it? That 60 second means 1 minute. So in 1 minute we calculate the heart rate. So from this derivation, we have adapted that formula, and applying that formula you can directly use, no need to go in this theory, but to understand how it was derived, you can use this formula. So one formula is 1500 divided by number of small square box between two consecutive R wave. So you see here, so here is your R wave peak, here is another one, here is another one. So if you take the distance, if you take the number of small square box between these two R, So how many will be there? The image is little bit blurred, but supposing that it falls exactly on this line, so it will be like 5, and here it will be 10, 15, and less than midway, so two small square box it could be occupying. Let me see here, and let me zoom it up. uh, it's still unclear, but it's occupying two small square box, it is pretty sure. It could be 2.5. Okay, let's assume that 2. So how much it will be there? Here to here there are 5, and up to here 10, 15, 16, and 17. Okay, so when you go here, so according to our formula what it becomes? Heart rate is 1500 divided by 1500 divided by 17, isn't it? So it will equal to how much? 1500 divided 1500 divided by 17. So it comes 88 point something. So we keep it 89. So heart rate is 89 beats per second. Since this is regular stripe, so another formula also you can use. So what is the next formula? As we have already discussed, so pick any two consecutive R waves. Suppose let's say here is your R wave and another is one is here. So what you do is that you come the another formula, that is 300, 150, 100. So in that formula, by applying that formula, so here to here you take 5 small square box. So pretty this it comes here, and likewise another it will come here, isn't it? And another it will come here, somewhere here. So you see here, so here to here it will be 300, here to here 150, and here 100, and here it will be 75. So the heart rate is basically between 75 and 100. So this is the another quick method to access how much is the heart rate, whether it is tachycardic or not. So 75 to 100, so it is pretty normal, and as we have already discussed, it is 89. So this is the just briefing to calculate the heart rate pretty quick. So any two consecutive R wave you can take. So here and here also you can take, and draw 5 small square box. So this one is here, so next one will be here, next one will be here, next one will be here, next one will be here. So you see here again, here to here it will be 300 heart rate, here to here if it goes 150, here to here it goes 100, here to here 75. So 75 to 100, between 75 to 100. So to quickly access, you can apply this formula. So about heart rate and rhythm we have clarified. Now we will be moving forward. Now we will find out whether the given ECG is under sinus rhythm or not. So to find whether it is sinus rhythm or not, we need to look at lead 2. So while looking lead 2, what we need to look at is we need to look at the P wave. So in lead 2, if P wave must be always positive to be a normal ECG or a sinus ECG, sinus rhythm ECG. So here you see in lead 2, P wave they are positive, so it is okay for us. And the another thing that you must understand is that to every QRS complex, P wave must precede QRS. So you see here in this rhythm stripe, this is your P wave, this is your P wave, this is your P wave, this is your P wave. And similarly, you see here, this is your QRS complex, this is your QRS complex, this is QRS complex, and this is another QRS complex. You see here, so you see here every P wave is preceding the QRS complex. So you see here every P wave is preceding the QRS complex. So this also clarifies the another criteria for sinus rhythm. Now another thing to look at is, so let me zoom here. So you see here, so this is P wave and this is PR segment. So altogether it is called PR interval. So when you look in rhythm 2, so this is your lead 2. So you see here it's like pretty much normal, and the PR segment it is occupying almost 2 square box, so which is also normal. So there is no any sort of any kind of AV conduction delay, so you can also say that. And the PR interval is also pretty okay. So this is we can safely say that it is normal sinus rhythm. Now we come to axis determination. So as we have already discussed in previous videos, so we will determine the axis here. So to determine axis, what I do is I take lead 1. So let me draw a bold one. So what I do is I draw lead 1. Okay, so lead 1 direction will be in this way. Let me draw the arrow form. So lead 1 will be this way, isn't it? This is our lead 1, and I will draw AVF. So I personally prefer drawing lead 1 and AVF. So in basic, if you go and revise basic fondas of ECG in my previous videos, then you will understand why lead 1 in this direction and AVF in this direction. So generally the lead are directed downward and towards the left respectively in lead AVF and lead 1. Now what you do is you see lead 1. So this is your lead 1. So you see here, let me draw it with circle. So you see here the QRS complex. This is our QRS complex. You see here the QRS complex, they have positive deflection. So what do you understand if they have positive deflection? If a given QRS deflection is positive, so what does it says is that, so you see here this is your 0, and that means origin. In lead 1 the vector is positive, so what will be the direction? So it will go like this. So it will go in positive direction. Since the arrowhead is the positive direction, so it will go here towards the left, isn't it? So looking at the magnitude, we draw up to here. Now when you take another example, that is, let me draw with brown color. So AVF, where is our AVF? So you see here in AVF, let me draw with circle. So in AVF also you see, in AVF also the QRS complex is positive. So when you draw its vector again, so this is your origin line, so it is positive, it means it is directed towards the vector, is directed towards the arrowhead. And you see the magnitude of QRS complex in lead 1 and AVF, if you compare, lead 1 is slightly less than AVF, so we will extend it a little bit lower, and this will be the vector representation of this form in lead AVF. Now the next thing what we do is we draw imaginary line perpendicular to this vector. So perpendicular line will be here, isn't it? If you draw angle there, so it will form here how much? So the angle here will be 90 degree, isn't it? So angle here will be 90 degree. And similarly, if you draw another perpendicular imaginary line from the tip of vector of AVF, so it will be forming somewhat like this. So if you see here, so here somewhere here it will be the perpendicular angle 90 degree. So you see here, so let me draw it with yellow color, or let us make it purple color. So you see here you see the two imaginary perpendicular line, they are meeting. So this is the resultant of QRS vectors from lead 1 and lead AVF. So when I draw the resultant, suppose I draw a resultant now. So when I draw the resultant, so you see the resultant will go in this direction. Let me draw it with a bold one. So you see here, this is our resultant newly formed vector. So you see here that we have drawn. So this is the newly resultant vector. So this is the resultant R, and this resultant R vector will show us the axis. So you see here, this is 0 degree, this is 90 degree. So it is lying somewhere between 0 and 90, which is of course between the normal axis of the given ECG. So here the ECG axis is also normal. So we have also dealt with that. So the vectorial axis is normal. So when vectorial axis will be normal, so pretty we can rule out that there is no any right ventricular hypertrophy or left ventricular hypertrophy or something like that, isn't it? And we can also determine the axis of individual atrium, but in this case again you see here, in lead 1 the P wave is positive, and in AVF it is also positive. So if you draw the resultant, so positive as like the previous ventricle one, it will be quite might be falling under the same axis, but we will not go to that. We will just focus on the ventricular axis first of all. learning at the basics.